So hi everyone and welcome to our video on improper integrals, which is the last leg of our discussion on the techniques of integration. So I'm pretty sure that if you scan through a typical textbook, you've probably seen integrals like these before. Those having limits or an upper limit or a lower limit of maybe infinity, and you might have found it strange that there would be integrals like those. But in reality, there are many use cases for integrals like these. So you see here those integrals in the orange box have, for example, the first one is from a lower limit a to an upper limit, which is positive infinity, which is quite a big range. You have here in the second one from negative infinity until b. Then you have here from the total range possible, that's negative infinity to positive infinity, so a very big range. And you have special cases here of this special cases of integrals which correspond to discontinuities. So we refer to these integrals as improper integrals, right? So we call them improper integrals, and these are integrals wherein there's a chance that the limit of the integral would not exist, and there's a chance that there would exist based on how we solve it. And we have certain rules that we follow. So for the first case, say we have an integral of a from an integral of f of x from a until t. So if that integral exists for any number that is t greater than or equal to a, then the integral from a, which is a lower number until infinity, of this function is just the limit of as t approaches infinity. So as that number gets larger and larger away from a, okay, of from a to t of f of x dx, provided, right, provided that the limit exists. So we can calculate for this integral in this format there. The same is true if we have, instead of this upper bound, we have a lower bound, which is here. And that integral exists for every number that is t, which is less than or equal to b. Then the integral of negative infinity until b of a function f of x is just equal to the limit as t approaches negative infinity of this integral here. Okay, the integral from t, which is the lower limit until b of f of x dx. And again, provided that this limit exists. So those are like the general cases because we have infinities and limits there, but we can also have improper integrals wherein it's one where the limits of integration, that's a and b. So for example, the limits of integration, those are those, right, are finite. So in this case, they're not infinity, so they're finite. But there's a chance that the function has an infinite discontinuity on that interval. And these two examples here are examples of that, right? So for the first one, the integrand goes to infinity as x approaches 0, right? So at an interior point of negative 1 to 1. So within this integral, somewhere within that area, there is a discontinuity, which sort of spoils everything, and we can't solve for it. While in the second one, the integrand goes to infinity as x approaches 0, which is the lower limit of integration. So you'll notice that there will be something that is relatively unsolvable, and we would need to take a limit for that. So I think to better understand it, we have to get into another concept, which is the convergence and the divergence of improper integrals, and then we'll solve it, and then I think you'll get it when we do the solving part. So there are two types of improper integrals. So we can call the improper integral convergent. Okay, so convergent if the limit exists. So if the limit exists, we can say that the improper integral is convergent. But if the limit does not exist, we refer to it as divergent. Okay, so we have those there. So I think to better get this concept, we just need to do an example, and that will shed some light on it. So determine whether or not this integral here is convergent or divergent. So we just solve for it using the condition that we learned. So this is the integral from negative infinity to 0 of e raised to x dx. And again, this is an improper integral, so we take the limit, right? So this is the limit as t. So we have a lower bound here, approaches negative infinity of the integral from t to 0, okay, e raised to x dx, right? And to solve this, this is just the limit, okay, as t approaches in negative infinity of e raised to x, right? The integral of e raised to x is just e raised to x, right? And we will evaluate this from t until 0, right? So if we simplify this even further, this is the limit as t approaches negative infinity of, if we first plug in the upper limit of integration, so that's 0 minus e raised to t, right? Now, if you notice, when t approaches something that's negative, so when this is a highly negative number, you'll notice that the value of this exponential will go closer and closer to 0, right? So we'll go closer and closer to 0. So this will be minus 0. But e raised to 0, that's just equal to 1, right? So this is going to be equal to 1. Therefore, the answer to this integral is 1. And since we have here a rational solution, this given improper integral is a convergent one. So this is a convergent improper integral. Okay, so let's try another example and then see whether it's convergent or divergent. So we have here the integral from 1 until infinity of 1 over x dx. So again, applying our basic rules, so the integral 1 infinity 1 over x dx, that's the limit, okay? In this case, we're now going to do until positive infinity of the integral of 1 until t of 1 over x dx, right? This is equal to the limit as t approaches infinity of, so if you take the integral of 1 over x, that's just ln x, right? So this is the limit of ln x evaluated from 1 to t, right? And if we simplify this, this is the limit as t approaches infinity of ln t minus ln 1, right? And we're going to evaluate this based on those, by plugging in this one. We have a t here. So as t approaches infinity, right, ln t is also infinity, right? If we let t approach an infinite value or keeps on growing bigger and bigger, that value approaches infinity. And if we subtract a small value like ln 1, that's still going to be equal to something that is infinity. So we have here a solution that is infinity. Therefore, this particular improper integral is a divergent improper integral. So we're gonna get into more examples in the next video, but I hope in this video you could already see how you can differentiate a convergent improper integral and a divergent improper integral. So with that, thank you for your attention, and I'll see you in the next video.